Hello, this is the next video in a playlist that I'm calling General Linear Models Design of Experiments. And within that playlist, we create little mini-series that deal with the different types of experimental designs. This mini-series, we're looking at analysis of covariance, and this is part 7 of a 9-part series. And here we're going to generically develop the least squares estimates for a balanced, randomized, complete block design with one covariate. Now, in the next 2 videos, we're going to do our illustrations of a couple different types of analysis of covariances. But in this design, we're going to stick with this. So as a reminder, the model is x star, beta star, epsilon. So it does fit into the general linear models arena. But we separate the design matrix into x and z, and where x deals with the ANOVA part of the design, and here we're doing a balanced, randomized, complete block design. And the z is, in this case, deals with a covariate, and so that should have a vector sign above it because it is a single observation, like this. So now, in part 2 of this little mini-series, we dealt with the column spaces of the design matrix here, and we noticed that if we add a well-chosen 0, we can kind of change it to look like this, and these models end up being 100% the same. But in this way, these 2 column spaces are orthogonal, which then helps us create and develop the structure behind some of these least squares estimates. So the beta parameters, or let me do this, the design matrix X has a column of 1s, X tau, and X beta. These deal with the treatment effects, and these are the block effects. The beta parameter is mu, tau 1 through tau A, beta 1 through beta B. The Z, so the one covariate we have, and these are linearly related to Y, but we center it, so it's a centered regression variable. Now, in what we do next, I'm going to follow the mini-series Randomized Complete Blocks ANOVA, and we're not going to rederive those results, we're just going to state them here. So if some of what we go through is too fast, I would highly recommend that you go through this video, and it's a several part mini-series. Here we're going to let perpendicular projection matrices J, M tau, M beta, and Mx equal their corresponding values. We also derived that Mx was M tau plus M beta minus J. And all this is derived in this video here. So now when we start breaking these least squares estimate up into smaller pieces and then combine them at the end, we get the following results. So Mx times Z is this. So remember, Mx was these 3 perpendicular projection matrices times Z, and it's a centered variable, right? So we take Z times Mx and we get a treatment mean, Z times MB, and we get a block mean vector, and then Z times J, we get what's called a grand mean vector. Now this times this, we get it back, so we actually get a grand mean. Here we get a grand mean, and then it's plus a grand mean. Well, this plus and this minus cancel, and we're left with just this. Notice there's 2 of those, so technically we combine those and put a 2. Now, I minus MXZ, we take the Z times each of those, and here, remember, it's a centered vector. So we get the original data minus the grand mean vector, because we're subtracting the mean off of each component. That's what this represents. And here we just derive that it's this. Now all the signs change because it's minus this. So all those little signs change. And I went ahead and put the 2 out front. Now, we have two of these minus one of them, so we're left with just one, and that's what this plus grand mean is. And then everything else carries down. And in scalar notation, it's this. So z is the actual data, the z, the covariate value. Z treatment mean deals with the treatment mean vector. So whenever it deals with, the treatment mean is the first index, so you have to subtract that mean off, and then the second index deals with block effects, so you have to subtract off that effect, and then we're adding the mean value to each component. Oops, sorry about that. Now we do the same for y instead of z. Here was z. Now y times each of those, we get this. And then y is just a vector of y values. And this one, we replace it with what it equals, m tau plus m beta minus j. And this helps us develop structure around that. So y times that, we get a treatment mean vector. We get a block mean vector, and then we get a grand mean vector. And don't forget to distribute that negative. Now, z transpose I minus mxz, this is idempotent, so we can take it times itself, but then we untranspose this, and then we just derived what these equal up here, or this. But this is vector product, so it's actually this times itself plus each component times itself, which is this. And we generically call that SSZZ, right? ZZ. Now, if this is invertible, this right here, then it equals its inverse. But this is a number. This is a vector, 1 by, something vector. This is something by 1, so it's a 1 by 1. It's a number. So the inverse is actually just take it to the denominator. And this is what we were generically calling SXZZ. Now we do the same, but instead of Z and Z, we do Z and Y. And this is idempotent, take it, and then untranspose the second piece, and we get this. And then this times this, remember it ends up being two, you can write them as two vectors, so it's a vector product. So we're summing the same components, from component 1 times component 1, component 2 times component 2, all the way down, and we get this cross product. And we call that SSZY. Now, the least squares estimate of the parameters associated with, or parameter associated with the covariate, there's only one value, so that's one value, it's not a vector, is this. And we call this SSZY and this SSZZ. And this is so similar to simple linear regression. Remember, this is a number. So if it's a number, then it's invertible. So you can take it to the denominator. So so if SSZZ is invertible, meaning it's a number, then the gamma tilde is unique. We get a unique value. And actually this is illustrated in the R examples, the next two videos that I do. It's actually kind of neat how it all works out. If this is not invertible, then the least squares estimate is not unique. But in most cases, this is invertible, and we get a unique solution for the gamma parameter. Now, in part 3 of this little mini-series, when we derived the least squares estimates, we showed that the least squares estimate for beta, which we call beta tilde, must satisfy this. Well, let's look at this a little further. So we take that into each of those, and then mx is this, m tau plus m beta minus j, and then when you take that into each of those, we get this, the treatment mean, the block mean vector, and the grand mean vector. And this we showed was this. And of course that's the least squares estimate. So what is so cool that beta tilde is not unique. There are an infinite number of these vectors that satisfy this. But what is neat is x beta tilde is unique. And this is actually the fitted model. So the fitted model is unique. And we illustrate this in our software. We come up with several different least squares estimates, and we show they're all different. But then when we pre-multiply it by x, the design matrix, they're all the same. All right, well, that's all I have for this video. Hope you enjoyed that. The next two videos deal with our illustrations in two different types of analysis of covariance. So hope you enjoyed it. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.